Hello everyone, I'd like to talk about a specific case of fusion in the task of language modeling. It is a follow-up to our previous paper on fusion in knowledge-intensive NLP and retrieval. The task at hand is autoregressive language modeling. As you probably all know, that simply means predicting the next word in a sentence. Here we have the sentence prefix Moctezuma finally faced the, and then the correct continuation from the data is conquistadors. The way we do this computationally is to use, for example, an LSTM model. It works by first turning the input words into vectors via an embedding layer, and then iteratively consuming word by word. At the end of each step, we take the last hidden state, and by applying the output embedding to it, we get a probability distribution over the possible continuations. We use this distribution to evaluate the model, but in essence, it tells us which word comes next. This can, however, be improved by using something which we call artifacts. Those are objects that are either retrieved or computed by some other model, and then fused into the main model. Here we are using a pre-trained language model which is perhaps not autoregressive, so it can be used to predict the next word. However, we can compute this representation of the prefix Moctezuma finally faced the, and then put this representation, the artifact, into our autoregressive language model. There are multiple ways in which the artifact can be fused into the model. For example, we may set the initial LSTM hidden state to this vector, or we may concatenate the final hidden LSTM vector with our artifact. Even though there are many ways the artifacts can be fused into the model, we distinguish primarily between early and late fusion. The two examples here show exactly that. Early fusion sets the initial hidden state to the artifact, and late fusion either concatenates, adds, or multiplies the artifact with the final LSTM state. The motivation for this is that you may leverage the representation strength of models, which are, for example, not autoregressive. And furthermore, it may not be a model at all, but rather something retrieved from a knowledge base, a database, or the internet. Specifically, however, in our experiments, we are working mostly with masked language models such as BERT. We measure the results on Wikitext and look at perplexity. That's a metric for language modeling for which the lower the number, the better. In this graph, the perplexity is on the y-axis, and the training epochs on the x-axis. We can focus on the highlighted rectangles and specifically follow the blue line, which is the original model without any fusion. All the other lines correspond to different fusion modes, and an intermediate observation is that they all improve the model performance. That means that the fusion models yield lower perplexities than the no fusion model. However, there are some differences. For example, multiplication of the last state converges much later in contrast to early fusion, which converges around epoch 40. It's also interesting that the early fusion doesn't perform as well as simple concatenation of the final state. One would think that the sooner the model has access to the extra information, the more it can utilize it. But our results show that this is not the case. One limitation that we found and that we need to acknowledge is that the more data you have, the less the fusion matters. Here on the y-axis is again the perplexity, and the x-axis is log-scaled amount of training data sentences. We can clearly see a trend that with more data, the difference between no fusion and fusion is getting smaller and smaller. Obviously, having a whole BERT model as a dependency to your smaller autoregressive model beats one of the purposes. Therefore, what we try to do is to start with a model that has access to this artifact, but then slowly reduce this access. In this figure, the blue line is a model without any fusion, and the red line is a model with concatenation fusion. They are clearly separated, and the model with fusion is under the blue line, which means it's better. In between is the VNOV model, with the yellow line. Every 20 epochs, we increase the dropout of the artifact. It starts as good as the full fusion model, but the more of the artifact we mask, the worse it gets until it converges to the no fusion model, the blue line. This means that we cannot easily get rid of the artifact dependency once we start the model on it. However, the silver lining is that we can observe a clear and quantifiable result of reducing the artifact contribution, and also that the performance is bounded well between the fusion and no fusion models. One motivation of this research is that it moves us in the direction of one of the open questions from our last paper. Namely, it provides a platform to answer questions such as how does the fusion help and what exactly does it internally do to the intermediate computations to make the predictions closer to the gold outputs. There's a short video on our last paper on artifacts which explains this in greater detail. There are many more experiments and details explained in the paper, and I would be very happy to discuss them with you if you had the time to read it. We discussed things such as speeding up the inference by querying the original model only sometimes, sources of artifacts, transfer between domains or correlations with human surprisal. For future work, we would like to see more methods to speed up the model inference while retaining the gains from the artifact access. The experiments should also be replicated on larger data and models to verify their validity, because we saw that the data size definitely has an effect. We did not dig deeper into answering the question how the fusion actually works, and I believe that both empirical and theoretical research can be done in this direction. Finally, in our paper, we mostly worked with masked language models and some trivial baselines such as TF-IDF. To further support our intuition that any relevant information-bearing artifact can be used to improve the model, more artifact sources should be explored. Regardless of all these missing pieces, we clearly saw that even trivial fusion models help with artifacts from masked language models, and that they have different characteristics. That's it. Thank you for listening to this presentation, and I look forward to your feedback on our research.